Okay, so let's start. The next speaker is Professor Zhiyun Cheng from Beijing Normal University. The title is on region crossing change. Please start.
Okay, thank you. Can you hear me?
Yes.
Okay, good.
Okay, please start.
First, I would like to thank the organizer for giving me an opportunity to give a talk here. And today, I would like to discuss some recent progress on region crossing change. Actually, which was originally partially proposed by Professor Carl himself. Okay, I would like to begin my talk with a question. First, I would like to discuss the notion of a hypergraph. By a hypergraph, we mean it consists of two sets, the vertex set and the edge set. In my talk, all hypergraphs are assumed to be finite. So the vertex set consists of some finite vertices, and the hyperedge set consists of finitely many hyperedges. For a hypergraph, a hyperedge is just a subset of the vertex set. So for a unit graph, an hyperedge, maybe I should say an edge consists of two elements because an edge has two endpoints, but in a hypergraph, it could be an empty site or just 1, 2, 3, 4, 5. So here we have a very simple example. Here we have three vertices, V1, V2, V3, and here we have three hyperedges. The first one, E1, is just the V1, and the second one is V1 and V2, and the third one contains all the vertices. So with a given hypergraph, we can define an incidence matrix, which is if we have n many vertices and m many hyperedges, then the incidence matrix is a m cross n matrix, and the entry Aij is equal to 1 if the vertex Vj belongs to the hyperedge Ei, otherwise it is 0. So for example, just for this hypergraph, it is easy to find that the incidence matrix has this form. So each row vector corresponds to a hyperedge. So this is E1, E2, and E3. So each column corresponds to a vertex V1, V2, V3. So now you have 3 cross 3 matrix here. I would like to remark that usually the incidence matrix is defined to be the transpose of this matrix, but since we just concerned with the rank of this matrix, so this is not a big deal. So by a state of a hypergraph, we mean a function from the vertex set to a set of two elements. Maybe we can regard it as Z2. So in other words, a state is just an assignment which assigns a 0 or 1 to each vertex. And also we can view a state as a row vector. And we say two states are equivalent if the difference between them can be written as the linear combination of some hyperedges. So here we just regard the state and the hyperedges are all row vector. So if you can find some coefficient, and each coefficient Ai is belong to is just a 0 or 1. if you can find such a linear combination, then we say these two states are equivalent. So the question is, how many non-equivalent states does H have? Actually, the answer to this question is quite easy, because you can find that if there is no hyper H, then we have 2 to the power of n different states. If we have one hyper H, then we have one relation. So the number of the non-equivalent states will be divided by 2. And by repeating this, you can find that the answer to the question is this. So in order to answer the question, you just need to calculate the rank of the incidence matrix. For example, for this very simple hypergraph, we can find that the rank of the incidence matrix is 3. So it follows that all the states of H are equivalent. So what does it mean? Oh, sorry. Sorry. So recall that H contains 3 vertices. Maybe we can say V1, V2, V3. And each of them, by state, each of them is assigned with 0 or 1. For example, we can choose, for example, maybe just 0, 1, 1. So after that, you can use the, maybe I should, sorry, I choose this is V1 and this is V2, this is V3. So we can use the first hyper H E1 to transfer this state to another new state, which is 0, 1, 0. And next we can use sorry. Let me assume this is V1, this is V2, this is V3. So we can use E2 to get a new state 1, 1, 1. So all the states of H are equivalent, means that you can use the hyper H to connect all the states. For the rest of my talk, I will show you some examples, and the solution of these examples can be translated into the question of calculation of the rank of the incidence matrix of some hypergraphs. Let us begin with a very trivial game, game 1. Game 1 means that in the incidence matrix, 1 appears just once in each column. So in this case, it is evident that all the non-zero row vectors are linearly independent. So in this very simple case, it follows that if there exists no empty hyper H, then the rank of this matrix is nothing but the number of the row vectors. So in this case, the number of non-equivalent states is equal to 2 to the power of n minus m. And all the states are equivalent if and only if m is equal to n. So this is actually a very trivial case, but I would like to choose it as the first game. So for the second game, I would like to discuss the case that 1 appears twice in each column of the incidence matrix. Actually, this game came from this question. Recall that a graph is we can choose a signed simple connected graph. Here, signed means that each edge is assigned a positive one or a minus one. And simple means that so there is no loop and multi-edge. Yes. Of course, the connected means just connected. So for a given signed graph, we can take an operation called the vertex switching. So vertex switching will reverse the signs of all the incident edges to the vertex. For example, for the first signed graph, if we take the vertex switching on this vertex, then this sign, this sign, this sign, and this sign will be switched. So we will get a new signed graph. And then we apply the vertex switching on this vertex. We will get the third signed graph. And finally, after taking vertex switching on this vertex, we will get a positive signed graph. So the question is, how many signed graphs are there over an unsigned graph up to vertex switching? We can translate this question into a language of a hypergraph. I mean, if we are given an unsigned graph G, then we can construct a hypergraph as follows. First, each edge of G corresponds to a vertex of H, and a vertex of G corresponds to a hyperedge of H. If Vi is incident with EI1 to EIS, then the corresponding hyperedge is nothing but this set Vi1 prime and the VIS prime. Then a signature, I mean a sign, is nothing but a function from the edge set to this set of two elements, and it can be written as a row vector. Actually, because this hypergraph, we just interchange the row of edge and vertexes, so it's easy to find that the incidence matrix MH is nothing but the usual incidence matrix of MG, and so they have the same rank. But the reason I write it in this way because I just want to use the language of a hypergraph. So the answer is, recall that our question is how many signed graphs are there over an unsigned graph up to vertex switching. So the answer is, first, the number of signed graphs is equal to this. Yeah. So in order to calculate the number of signed graphs, it is sufficient to calculate the rank of the incidence matrix. And it was proved by Nasra, Lulavo, and Spina in 2015. The rank of a connected graph is equal to, actually is one less than the number of vertices. Actually, the proof is quite easy. For example, if we have a connected graph, just like this. So it means that it is easy to find that. Notice that now in this case, each vertex corresponds to a row vector, and the sum of all the vertices is equal to 0. I recall that we are working over the coefficient Z2 because each edge has two endpoints. So these two endpoints will have two contribution to this edge. So 1 + 1 is equal to 0. Modulo 2. So it means that the sum of all the vertices is equal to 0. And the key point here is this is the only relation. So it follows that the rank of it is equal to the number of vertices minus 1. And it follows that if we want all signed graphs over a connected graph are equivalent, if and only if this graph is a tree, because just in this case, this is equal to 0. So another question is, when a scientific graph is switching equivalent to a positive graph, just like in this example, we show that this scientific graph is switching equivalent to a positive graph. So actually, this is a very classic result proved by Harari about 17 years ago. He proved that if G is a simple scientific graph, then G is switching equivalent to a positive graph if and only if each cycle of it has a positive sign product. And equivalently, if and only if the vertices of G can be partitioned into two subsets. For example, this is one subset, and then this is another one. So we have some vertex here, we have some vertex here. And if an edge connects the vertex in different sets, then the sign of it must be negative. And this kind of edge will have the sign positive. So if and only if the graph G has this form, then it is switching equivalent to a positive graph. And this kind of scientific graph are called balanced. Actually, in the theory of scientific graph, the balanced graph are very important. So this is the second game, because each edge has two endpoints. So in this case, one appears just two times in each column of the incidence matrix. Okay, so let's turn to the game 4. So maybe you would like to ask where is game 3? We will come back to game 3 later, but let us first talk about game 4. In game 4, 1 appears 4 times in each column of the incidence matrix. And in this example, this is a real game. Let me tell you a game called the Range Selected, which was proposed by Professor Kawauchi and Shimizu and Kishimoto about 10 years ago. So how to play this game? First, we assume that we are given a flat node diagram on a plane, just like this. And each crossing point is equipped with a light bulb. Yeah, so we have 3 light bulbs here, and some so we can click a region to switch those light bulbs on the boundary of this region. And the aim of this game is to light up all the light bulbs. So for example, if in a if we are given a state like this, then we can click this region. Then by clicking this region, we just turn on this light bulb and turn off this light bulb. So we will get a new state like this. And we can then click this region. So we are down here, and all the light bulbs are on now. So the question is, when can we achieve the goal? Is it true that for any node diagram and any state, we always can achieve the aim? Actually, the answer is yes. So first, I would like to talk about so-called the region crossing change, which was suggested by the title of my talk on the two-sphere. In 2010, Kishimoto proposed a new local operation called the region crossing change. So what is region crossing change? Region crossing change is a local operation on a node diagram or link diagram. So if we take a region crossing change on a region R, then we just switch all the crossing points on the boundary of this region. For example, if we take a region crossing change on this region, then this crossing point and this crossing point will be switched. So we will get a new node diagram. So this is a red-handed trefoil, and this is a diagram which is unknot. Kishimoto asked the following question: is region crossing change an unknotting operation? For example, in this example, we can show that we can use region crossing change to unknot the red-handed trefoil. But we know that first is the trefoil has infinitely many diagrams. Can we always achieve our aim for any diagram of it? And how about other knots? So in order to answer this question, I would like to introduce a notion called the region crossing change admissible. So assume we have a link diagram D, and we choose some crossing points of it. We say they are region crossing change admissible if one can switch these crossing points and preserve all others by a sequence of region crossing changes. For example, these two crossing points are crossing change admissible because we can use this region to switch these two crossing points. Of course, these three crossing points are also region crossing change admissible because we can use this region to switch off them. The main result of Ayaka Shimizu is that she proved if we have a node diagram and we choose any crossing point of it, then this crossing point is region crossing change admissible. So in other words, crossing change can be realized by region crossing change. So as a corollary, we know that crossing change is an unknotting operation, so it follows that region crossing change is also an unknotting operation for knots. So it means that actually this result does not depend on the choice of the node diagrams. So for any diagram of a trefoil, you can always find some region such that by taking region crossing changes on these regions, you will get a new diagram which represents the unknot. Okay. Here we have some remarks. If one have a unknotting operation, one can consider the corresponding unknotting number. It is very natural to define the unknotting number of region crossing change to be the minimum number of region cross change needed to unknot knot K among all the node diagrams representing this knot. However, if we choose this definition, each non-trivial knot has a knotting number 1. Actually, this is an older result proved by Enda in 1992. And during the past 10 years, Ayaka's result has been extended to many other cases. For example, integral region crossing change, which replaced the coefficient Z2 to Z. And Katakami also studied the region crossing change on virtual node diagrams. And later, Shimizu also studied that the region crossing change is an unknotting operation for special graph diagrams and for the region Friesen crossing change, which means that by taking the region Friesen crossing change, you switch all the crossing points not on the boundary of this region, and the crossing point on the boundary of this region will be preserved. And this is also an unknotting operation. And she also showed that region crossing change is an unknotting operation for theta curves, something like this. Okay, so this is the result for node diagrams and some generalized objects. A simple observation is that region crossing change is not an unknotting operation for links. For example, for the standard diagram of the Hopf link, here we have 4 regions. Here R1, R2, R3, and R4. It's easy to show that whatever you do, you can just get this kind of diagram of half link, but you cannot get a node diagram which is a trivial link with two components. Yeah. So the following question is, for which kind of link diagrams region crossing change is an unlocking operation? In order to answer this question, we can go back to construct a hypergraph. So for link diagram, and we use C1 to Cn to denote the crossing points and R1 to Rm to denote the regions. Here we always assume that this link diagram, we assume it is connected. Yeah. So now we can construct a hypergraph H such that each crossing point corresponds to a vertex of this hypergraph, and each region corresponds to a hyper edge, such that if we have some crossing points on the boundary of this region, then the corresponding hyper edge contains all the corresponding vertexes. And now the answer is the number of non-equivalent link diagrams up to region crossing change is equal to 2 to the power of n minus the rank of the incidence matrix. So in order to answer this question, we are sufficient to calculate the rank of this matrix. This is an example. So if we consider the Bromine ring, and now we have 1, 2, 3, 4, 5, 6 crossing points, and we have 8 regions. So now we will get an incidence matrix like this. So for example, C, region C, it had on the boundary, we have crossing C1, C2, and C5. So you will have a row vector such that the first place, the second place, and the fifth place are 1. And here we have 3 zeros. Because we assume that the link diagram is connected, it is easy to find that the number of regions is 2 more than the number of crossing points. So this matrix has the form of C plus 2 cross C. And now we can restate Ayaka's result as if D is a node diagram, then the rank of this matrix is equal to C. For example, if you have, so it means that the rank is nothing but the number of crossing points. Of course, this is correct for just node diagrams. So what about the general case? In a joint work with Professor Hongzhu Gao, we proved that if we have an n-component link diagram, also we need to assume that this link diagram is connected, then the rank of it is equal to C minus n plus 1. C plus minus n plus 1. So if n is equal to 1, we just recover Ayaka's result. Yes. Okay. Yeah, because Ayaka's result says that the rank of it is equal to C. Okay. So here is a complete answer to Kishimoto's question. If we have 2 link diagrams, of course, we need to assume that the shadow, I mean the projection of these 2 link diagrams are the same. And under this assumption, they are related by a sequence of region crossing changes if and only if for each I, the linking number between I and other components, they have the same parity. Yes. So for each I, they need to satisfy this condition. And in particular, region crossing change is an annotative operation on a diagram of a link diagram if and only if this link is proper. By proper, we mean that for each component, the linking number between it and other components is an even number. Of course, it also follows that actually the result does not depend on the choice of link diagrams. Okay, so this is the answer to Kishimoto's question. Next, I would like to discuss some recent results about region crossing change on a Hydrogenous surface. First is a warning. From now on, we will make a little modification on the definition of region crossing change. Assume we have an orientable closed surface with genus G, and L is a link diagram on this surface. And we choose a region R, and if for a crossing point C, if R appears K times along this crossing point, then we will, by region crossing change on this region, we will switch the crossing point C K times. So for example, in this very simple diagram, because if we consider this crossing point C, because the region R, I mean the unbounded region, appears 2 times along this crossing point. First time, 2, 1, 2. So we will, by take region crossing change on this region R, we will switch this crossing point 2 times, which means that it is preserved. But in the original definition of Ayaka's region crossing change, because it is on the boundary of this region, it will be switched. This is the Ayaka's definition. I have to say, the reason why we change the definition a little bit is because we don't know how to handle the original definition. So it is too difficult for us. So we just make a little modification on the definition. So under this new definition, we can also define an incidence matrix for each link diagram on a surface. For example, here we have this is a torus. Of course, we need to glue this line with this line and this line with this line. So this is a torus, and we have 2 regions here, R1 and R2, and we have only one crossing point here, say C. So now we will have a 2x1 matrix, and because R1, R2 both appears 2 times along this crossing point, so you will get a matrix like this. For the second example, this is a 2 torus, and we have only one region here because this just one. Actually, they are the same region, and we have only one crossing point here, C. So this region appears 4 times along this crossing point, so we'll get a 0 matrix. Also, the number of non-equivalent link diagrams is equal to C to the power of 2 to the power of C minus the rank of this incidence matrix. So we need to calculate. C minus the rank of this matrix. However, it is not easy to calculate it. Instead, we find that we call that this matrix has the form R cross C. We found that we don't know how to calculate the difference between C and the rank, but we found that the difference is between R and the rank. R denotes the number of the regions, the integer r minus the rank of the incidence matrix is a homotopy invariant. It means that you can apply some homotopy to a link diagram, and this integer will be preserved. So it follows immediately that for some very simple case, for example, for the two-sphere, we don't let any neural diagram is homotopy equivalent to a trivial circle on a two-sphere. So in this case, we can also show that each crossing point is region crossing change, of course, under our new definition. And hence, it is also an annotating operation. Actually, this is not a new result. I think you can you even can get this result from the Alexander's first paper and the definition of the Alexander polynomial. You just need to replace the symbol t with maybe -1 in the matrix defined by Alexander. You can find almost the same matrix here. And so the difficult point in Ayaka's proof is you need to handle the so-called negative crossing point. Under this definition, the result is quite easy. So this is the two-sphere case. And for torus case, we can also calculate the rank of the matrix, which depends on the greatest common divisor of P and Q is even or odd. And because we know that on the torus, we can use some homotopy to transform a node diagram into a standard form. For example, this is the I can say T12.8. Actually, this is a node diagram, but the homology class can be written as 12m plus 8l. M is the meridian, L denotes the longitude. So for the two-sphere and the torus, it is easy to calculate the rank of the incidence matrix. But for Hydrogenous, even the homotopy class of node diagram is very difficult. So the general case, the answer is if we use R to denote the standard generator of the first homology group of the surface, and let L be a link diagram, and we can write each component as a linear combination in this form, and here Bij denotes the coefficient. And now we choose all this Bij, and now we can form a new matrix N, which has the size of N cross 2 times G. With this new matrix, we need two lemmas here, but I don't want to explain it. So let's just skip it. The main result is this is a joint work with some undergraduate students in our department, and we show that for an orientable closed surface with genus G and L is an unconvoluted link diagram, the difference between R and the rank is equal to N plus 1 minus the rank of this matrix N. So in particular, for if G is equal to 0, so in this case, the rank N is equal to 0 because there is no homology here. So we can the result can be recovered because rank MH is equal to R minus N minus 1. Yeah, or you can say it is because R is equal to C plus 2. So it's equal to C minus N plus 1. Okay. So this is the result on the Hydrogenous surface. I guess I have 10 minutes. So in the next 10 minutes, I would like to, okay, oh, sorry. Here we have some remarks here. the problem of region cross change on higher general surface, I think it was first considered by Dasbach and Russo in 2018, but they have some assumptions on the link diagram. For example, they need that the link projection of the link projection is cellularly embedded. It means that each region is homotopy to a disk, and they also need to assume that the link diagram means checkpoint fashion coloring. But our result does not need these assumptions. And in their work, they also calculated the number of non-equivalent link diagrams, and their result can be written in this form: 2 to the power of 2g plus b. Here, b is the dimension of the color of a map. But I don't want to go to details of the definition of this phi. But actually, these two results just gave you the same information. Yeah. Okay. So this is the last game. I would like to discuss the case where 1 appears 3 times in each column of the incidence matrix. In the last game, why 1 appears 4 times in each column is because locally we have 4 regions around a crossing point. So because each law diagram or link diagram can be regarded as a planar 4-valent graph. So in this case, we just consider planar 3-valent graphs. Let G be a planar 3-valent graph on the 2 sphere and without bridges. So it means that this kind of edge it does not exist. Yeah. The reason is we want the dual graph of it is provides a triangulation of the 2 sphere. So we assume that it has no bridge. And by state of it, just as before, we just use 0 and 1 and assign it to each vertex. And region crossing change means that we switch all the vertices lying on the boundary of this region. And the 2 states are equivalent if they are related by some region crossing changes. For example, this is a complete graph K4. And here we have 0, 0, 1, 1 on these vertices. If we take the region crossing change on this region, then 1, 0, 0 will be switched to 0, 1, 1. So we'll get a new state. So the question is, how many non-equivalent states does G have for a given planar 3-valent graph? This is the answer. Assume we have a planar Trivalent graph of order n, and n we assume that it is greater than 4. If n is equal to 3, the case is quite easy because now in this case we just have when n is equal to no n can be n can be, for example, 2, we will have a zeta graph, but this case is very easy. So we just assume that n is greater than 4, and the number of regions is m, and so the result is the number of non-equivalent states of G. If all the regions are even, the result has this form, and if there exist some other regions, but none of them are adjacent to each other, and we also need another condition. So we need this condition. So what is G here? G is the fundamental group of the complement of the other regions. and H is a subgroup of the symmetry group of order 3. It contains the E and the element which switch 1 and 3. This is a subgroup of the symmetry group of degree 3. I have 5 minutes, so I will give you a very sketch proof on why we need to consider the a region is even or odd. And let me tell you what is the definition of even is even. It means that, for example, if a region is even, it means that the number of edges of it is even, because this is even, and this is a odd region. Yeah. So how to prove this? Again, first we need to translate the question into a question of a hypergraph, and we can construct a hypergraph as follows. The vertex of this hypergraph is just the same as the vertex set of the planar graph G, and each region corresponds to a hyper edge. If this this vertex is on the boundary of the region, so the corresponding hyper edge has the form like this. And also the answer is the number of non-equivalent states is equal to 2 to the power of n minus the rank of the incidence matrix of this hypergraph. So we need to calculate the rank of this matrix. This is an example, just like before here. Each row corresponds to R1, R2, R3, and R4, and each column corresponds to V1, V2, V3, and V4. Okay. In order to answer this question, we need to consider a J3 coloring. So what does it mean? If we consider the dual graph of this graph G, we use G prime to denote the dual graph, and this is nothing but a triangulation of the two sphere. And if we choose a triangle, for example, this is a triangle, and we use 1, 2, 3 to color the vertices of it. For example, 1, 2, 3, and we can extend this coloring to some other adjacent triangles. For example, if this is another triangle and the condition is adjacent vertices will receive distinct colors. So because this vertex is adjacent to this one, so it has to be colored by 2. And then you will have this 1, 3. And so you can extend this coloring to some other triangles. But the key point here is, for example, if you want to begin with this triangle and extend it to this one, you have 2 choices. You can use this approach, or you can use this approach. The key point here is, if this vertex point is even, then this coloring extending is well defined. But if it's odd, you will meet some problem. So this observation tells us that we can, if we fix a coloring of a triangle and a sequence of adjacent triangles which begin and ends at the same one. For example, this is the first one, and we can find a loop. And go back. So a loop will give you a recoloring. If there is no odd crossing point here, so this recoloring is just the coloring of is just the original coloring. But if we have some odd crossing, we have some other vertices here, you maybe will get a new coloring. So this will give you a group homomorphism from the fundamental group of the complement of the other vertices to the symmetric group of degree 3. So this is the definition of the group homomorphism phi. And from a global J3 coloring, we can get a global J2 coloring by replacing 1 and 3 by 1 and 2 by 0. And so what is the relation between this J2 coloring with our question? The question is, a global J2 coloring will give you a solution to this function. And now this kind of J2 coloring will tell you how to calculate the rank of this matrix. Okay, this is the last remark. A very interesting case is it is an odd result that if a triangulation of the two spheres admits only two odd vertices, then they cannot be adjacent. For example, yes, this is a very simple triangulation of the two spheres, and this is other vertex. This is other vertex, and all others are even. So in this case, you find that these two other vertices cannot be adjacent. They cannot be connected by an edge. And this result was first proved by Fix under the assumption of the four-color theorem. And in 1978, and we all know that during almost the same time, Appel and Haken proved the repeated four-color conjecture. But recently, Izmestiev, he reproved this result, but without using the four-color theorem. But as a corollary, we can show that if a triangulation of the two spheres means only two other vertices, actually they must be compatible. So what is the meaning of the compatible? It means that assume this is an other vertex and this is another other vertex. Choose a triangle here, and we can use the coloring 2, for example, 2, 1, 3. And now we can choose a path from this other vertex to this one. And by compatible means that this path will induce a coloring to this triangle, and this other vertex must be colored by 2. It means that they are compatible. Otherwise, they are not compatible. So this is a little stronger than the result, because if these two other if these two odd vertices are adjacent, it means that they must be in the same triangle. So if this is 2, this must be 1, 3 or 3, 1. So they can't be compatible. So our result just can be regarded as a little enhancement of the result by them. So I'm sorry. Let's work. Thank you.
Okay, thank you very much. So there is a question or comment? Yeah, your survey is a very detailed region crossing change for every version you state.
Actually,
very nice.
I just want to study the region crossing change problem on general planar graphs, but I don't know how to deal with this general case, so I have to add some restrictions. So we just consider 3 variant graphs. Yeah. But I think there should be an answer for the general case.
Thank you very much for your nice talk. Other questions there is? Okay, thank you very much.